Hi everyone, and welcome to the next talk in our afternoon's data science session. Here with me is Sefik, and he is a developer of the DeepFace face recognition library, and he has more than 10 years programming experience. And so, Sefik, welcome. Um,
Hello.
the stage is
Thank
yours.
thank you. I'm going to present my slides. I hope you can see it. You can see my screen. Hello, everybody. Thanks for coming. I just want to thank first PyCon Sweden organizers and the team for inviting me, and also my employer, Yapı Kredi Technology, for supporting me to come here and talk. Today, I'm going to talk about facial recognition, but we will focus on facial recognition as an end-to-end pipeline. The pipeline term is important here. Besides, we will also require large-scale and highly scalable pipelines. And let me introduce myself first. This is Sefik. I'm a software engineer at Yapı Kredi Technology, and I'm a contributor of many open source projects. In particular, I'm the creator of DeepFace package for Python, and I'm still maintaining it. That's highly adopted by the open source community, and today it has 2,000 plus stars on GitHub and 250,000 plus installations on Python package index PyP. This is because I'm talking in this conference today. I have a personal blog, sefix.com. I write here technical tutorials, mostly related to programming. Also, I'm creating online content on YouTube. By the way, I appreciate if you subscribe my channel. You can find me with my exact name. Finally, you can find me on Twitter with my surname as Serengil. If you mention me about anything during this talk, I promise I'm going to answer. And let's talk. Let's start. 1 in 1 million. This is the probability that a random person could look at your iPhone and unlock it using Face ID technology. What does this probability mean? If you buy, for example, 5 tickets a week for a year, then the chance of winning the current California State Powerball Lotto game would be same. This is really challenging. So it seems that just Arya Star can fool your Face ID technology. That's just a joke. Let's begin with the technology behind facial recognition. Neural networks, and especially convolutional ones, dominate computer vision studies recently because CNNs are very good at detecting face patterns in visual data. So facial recognition models are mainly based on convolutional neural networks. And suppose that you have a data set consisting of 100 identities, and each identity might have multiple facial photos. Then we will build a CNN model, and its output layer should have 100 nodes, because the facial database we have, it has 100 identities. And when we fit the images of Angelina Jolie, that's the first identity of our dataset, its output, its corresponding output should be 1, and others should be 0. And neural networks will tune its weights based on this input and outputs. Similarly, I changed the image with Jennifer Aniston, and when we fit the images of Jennifer Aniston, we set the corresponding output to 1 and others to 0, similarly to the previous one. And neural networks continue to tune its weights. And in this way, we define the facial recognition as a regular classification task. There are 100 outputs. We already know that CNNs are very good at classification, and we can guess this approach is going to work. But what if a new person would join into your database? Suppose that Katy Perry joins your database. We can add a new node corresponding to Katy Perry and into the output layer, and that's going to be 101 nodes in the output layer. But this is not going to work because our model structure is changed firstly, and our model will become more complex when a new member joins. We need to retrain the model always, and we won't have a centralized model. It's a decentralized, and each company should train its own facial recognition model. The question is that what if the newbie model underperforms? It's not guaranteed, and we really something different in this case. As an alternative approach, we won't add a new node to the output layer, so there is no corresponding node for Katy Perry in this case. And once you feed the facial image of Katy Perry, notice that the network haven't seen the any image of Katy Perry before in the training stage. When you feed the facial image of Katy Perry, the network will produce an output for her anyway. And we will call this output probas as vectors or vector embeddings. And we will use those embeddings in a facial recognition task. We expect that vector embeddings of same person should be more similar than the embeddings of different persons, and we can formulate the similarity with the high school math. Please remember the Euclidean distance formula. This is not the only way, but it's very easy. That's why I chose it here. We need to find the sum of the square difference of dimensions to calculate the square distance. This is an example for three-dimensional space. And face recognition models actually produce vectors with hundreds or thousands of dimensions. This formula is still applicable for multidimensional vectors. So we have the distance values between vectors and corresponding facial images. But how to determine they are same or they are different? This graph shows the distance distribution for both same person and different persons. The distance values for same person seem to be less than the distance values for different persons. Here we can determine a threshold value based on the distribution graph. For instance, we will verify pairs if the distance value is less than the threshold value 4. Here you see the distance values between the image pairs of Emilia Clarke and Lina Headey. If we set the threshold value to here 4.16, then we can verify all instances correctly. Even though daily appearance of Emilia Clarke and her role in the Game of Thrones don't look like each other, our model can verify them. So if we apply this approach, we would have a generalized model, and we don't need to retrain the model anymore when a new member comes into our database, and we will train it once and use it always. You can use my model as well. It's a generalized one, and model complexity is always the same. You might be familiar with the labeled face in the wild dataset. It's a de facto standard for facial recognition studies. And all researchers of the facial recognition work tested their model on this dataset. And human beings have 97% accuracy on this dataset, whereas Google FaceNet, ArcFace, DLip, or BGG Face of Oxford University, they already reached and passed that level of accuracy. Also, detection and alignment are some important pre-processing stages of facial recognition pipelines, and experiments show that pre-processing increases the face recognition accuracy dramatically. Nowadays, we have a very powerful face detectors, and you are seeing the result of retina face model in this illustration. It's a deep learning based model, and its robustness comes here. Its detection performance in the craft is amazing. It can find even the ones in the back rows, and the detector also finds some facial landmarks such as coordinates of the eyes and nose and mouth, and we can use those coordinates of landmarks to align faces. To sum up, there are 4 common stages of a modern face recognition pipeline: detection, alignment, representation, and verification. We mentioned all those stages from now on. And luckily, you don't have to do any of those stages manually. And DeepFace package for Python handles all of those stages in the background. And you are able to run facial recognition with a few lines of code. We will mention it. You just call the verification function in the DeepFace interface and pass the exact paths of image pairs as shown in this code snippet. By the way, you can pass, instead of exact images, you can pass NumPy arrays or base64 encoded images as well. But exact image paths are the easiest one. Then it's going to return the decision that they are same person or they are different person in the verified key of the result, and also some additional fields such as the distance value and the threshold value to determine. And that's a true positive case. DeepFace package for Python actually wraps many state-of-the-art and cutting-edge facial recognition models, such as VGG face model. That's a face model of Oxford University. Google FaceNet model, DLIP, ArcFace, Facebook DeepFace, and DeepID. Notice that most of those models already reached and passed the human level accuracy. Besides, it wraps many cutting-edge facial detectors or face detectors, such as OpenCV, SSD, MTCNN, DLIP, and RetinaFace. Here, RetinaFace and MTCNN are the most robust ones, but they are slower than OpenCV. So if you need speed, then you should use OpenCV or SSD. But if you need high score, then you should use RetinaFace or MTCNN. And you can switch among any face recognition model or face detector with a single line of argument. All functions except optional model name and detector backend arguments in DeepFace interface. And the default face recognition model is VGG face, and default face detector is OpenCV. So if you don't mention anything, then DeepFace will use VGG face and OpenCV pair, but you can switch those models and detectors, as I mentioned. Moreover, face recognition requires to run face verification many times, actually, because we verify an image pair are same person or different persons. But if you are looking for an identity in a large scale data set, this is face recognition, and you have to apply face verification many times. Luckily, DeepFace can do it in the background as well, and you should use its find function. And you should mention the identity that you are looking for in the image path argument of the find function, and set your database path to set your facial database in the DB path argument as well. In this case, it's going to return the identities it found. For example, I fit the image1.jpg in the left side, and it returns the 3 images of that person, Angelina Jolie, from our database. And we do it with a single line of code. Just we call find function. In addition to this, in addition to its face recognition module, DeepFace has a facial attribute analysis module as well, and we can analyze apparent age, gender, emotion, and race ethnicity of a facial image. In this way, we plan to fight with the biased data in the training of facial recognition. Also, we intend to decrease the search space with those demography information in face recognition studies. As seen, it analyzed the apparent age, emotion, gender, and race of those 4 images. By the way, its score is plus and minus 4 years for age detection, age prediction, and its score is 97% accuracy and also precision and recall for gender prediction. So if you have an image pair and you want to learn they are same person or different person, then this is going to be a face verification, and its time complexity is going to be O1 in the big O notation. On the other hand, if you want to look for an identity in the database, then that's going to be face recognition, and it requires to run face verification many times. Then its time complexity is going to be ON in the big O notation, where n is the number of instances in your database. ON is problematic when n becomes really big. Consider it's millions or billions. But I will ask a question. Have you ever wondered how Google run its reverse image search? Because I fit this image on the left side, Angelina Jolie, and it returns those images of Angelina Jolie in milliseconds. We know that Google is using a CNN model to convert images to embeddings. We guess it. And then it will return similar images with close embeddings. But Google indexed 100 billions of images. And how can it perform a query in milliseconds? That's very challenging. Do you think it's related to hardware the Google has? Similarly, Facebook image tag module, please consider it. That module applies same procedures. When an image ad, even if the other is not your connection, its face recognition module can find you in seconds. Notice that Facebook has billions of users and probably 100 billions of images. But how can Facebook perform that query in milliseconds as well? Is it related to the hardware Facebook has? Elephant is the iconic mascot of Hadoop. You probably understand where I'm going to go. Big data technologies such as Hadoop is much faster than the regular relational databases, but still that's a challenging task for both Google and Facebook to perform that complex queries in milliseconds. Here, a well-known Turkish photographer, Araguler, mentioned that if the best camera had taken the best photograph, then the one would be the best novelist who has the best typewriter. Similarly, query performing times should not be related to the hardware Google or Facebook have. They are running intelligent algorithm. They are running approximate nearest neighbor algorithm instead of KNN, K nearest neighbor algorithm. That's why the complexity becomes really small in those tasks. Well, because the complexity of KNN algorithm is ON, but the complexity of this approximate nearest neighbor algorithm is, as I remember, log n. Spotify nowadays uses that algorithm to recommend playlists as well. Currently, we have Spotify Annoy framework. It's actually the acronym of the approximate nearest neighbor. Oh yeah, Facebook has its face framework, and it's the acronym of Facebook AI similarity search. Similarly, we have an mslib library to run approximate nearest neighbor algorithm, and it's the acronym of non-metric space library. And finally, Elasticsearch actually wraps an mslib, and you can use it with highly scalable functionality. And this algorithm has a very small time complexity, but it applies heuristic approach. That's why you might sum close vectors. For example, in this illustration, you can see the font area, but it misses some vectors in this space. By the way, you can use the DeepFace framework to extract facial embeddings as well. And you pass the exact path of an image, then it's going to return a multidimensional vector. For example, Google FaceNet model returns 128 dimensional vectors. And you can store the output of those output vectors in the technologies we are going to mention. Here we are going to discuss the recommended tech stack for face verification and face recognition perspectives. If you are going to run face verification, then remember that the time complexity of this task is O1. And please consider this use case. We will log in to a mobile application of a bank, and bank should store facial embeddings of its customers in a data store. You can first store the vector embeddings in relational databases. But as a better way, you can store your embeddings in key-value stores, such as Redis or Cassandra. Why? Relational databases are good at storing and collecting relational data, but here we just need an embedding of a customer in a query. In this case, relational databases cannot work as fast as key-value stores. Notice that face verification is a subset of face recognition, so you can use the same tech stack of face verification in face recognition tasks as well. But when data size becomes big, those are not going to work. If your task requires high confidence, I recommend you to use NoSQL technologies such as Hadoop, Hive, Spark, because they are good at running K nearest neighbor algorithm. For example, you might think that you are going to search a guilty photo in a citizen database. You should use KNN algorithm because ANN algorithm might mess some identities. On the other hand, if your task requires high speed instead of high confidence, then you should use ANN solutions. For example, reverse image search of Google or image tag module of Facebook are some examples for applications of ANN. So a review of modern facial recognition pipeline has been done in this speech, and the description of the developed lightweight DeepFace framework has been made in my talk. DeepFace makes face recognition very easy and simple. If you are able to run facial recognition with a few lines of code. We then mentioned how to use DeepFace with some accelerating technologies to make it highly scalable for large-scale data. I thank you all for watching. If you have any questions, I will be happy to answer.
Hi, thank you, Sefik, for a comprehensive overview of the modern face recognition and face matching techniques. There is one comment that you would like to answer, perhaps. So there is a Milbus that wraps face as well. Could you comment on that, maybe?
Actually, this is not a question. Milbus is an alternative tool for ANN tools, and it wraps Facebook Face framework. And as I remember, it wraps NMS as well, but I haven't tried it before. But you can use Milbus as an alternative ANN solution as well.
All right, thank you. I have a question myself. This solution of yours, it wraps around pre-trained NN models. The question is, using your framework, is it possible to deploy an application on, say, the mobile phone? Or is it only like for desktop environments?
I haven't tried it, but you should use, for example, TensorFlow Lite, because the DeepFace framework depends TensorFlow framework, and if you are using TensorFlow Lite, you are able to run DeepFace on mobile application as well. By the way, DeepFace has an API service. In other words, you deploy DeepFace as a service, and in your mobile application, you can call its API. In this way, you don't have to build and run facial recognition models in the mobile side.
All right. Thank you. Thank you for an excellent talk. And thank you guys all for watching. And please join for the rest of today's data science section. Bye-bye, Sefik. Thank you.
Thank you very much.